On the topic of applications of derivatives, and we're going to be talking about like increasing and decreasing functions. And we're then going to talk about maxima slash minima, optimization problems. And then related rates. Hopefully, I think I might be covering, and then curve sketching. So I might have been covering that the whole time, but what I have is increasing, decreasing functions, maximum, minimum, optimization problems, related rates, and curve sketching. So let's first talk about increasing and decreasing functions. So what we have is some observations. So there is a picture that they drew on these notes here. Talk about intervals of increase, intervals of decrease. The point being is, if you have a function, the derivative is positive if it's increasing, and the derivative is negative if it's decreasing. That's really the gist of it. So I'm not going to draw that out. In fact, I'm just going to jump straight to the meat and potatoes, which is the definition of what increasing and decreasing is. And what that is that it's increasing if x1 is less than x2, x1 and x2, and then f of x1 is less than f of x2, and it's decreasing if x1 is less than x2, then f of x1 is greater than f of x2. That's when it's decreasing. I guess we haven't even just take a look at how long this lecture is. 7 more slides. So yeah, before I just cut the video, probably keep going, we're only at 3 minutes in, we can just cover this topic, that if f prime of x is greater than 0, then we're increasing. And if f prime of x is less than 0, then we're decreasing. That's it. So now we can look at some examples. Like a parabola that opens up. So you have something like this, right, that opens up. Like this. Right. You see that it has a minimum. Okay? For f of x, we have x squared. That's the basic of a parabola. And then f prime of x equals 2x. So what happens is that f prime of x is greater than 0 between 0 and infinity. And f prime of x is less than 0 from negative infinity to 0. So it's decreasing on this interval. This is increasing, and this is decreasing, right? Because the slope is decreasing on this interval. On this interval, it's increasing. That's what's happening. And if you look at this one, this one's actually always increasing if I do f prime of x. There's no value that I could put in there in the derivative that would make it negative. So that's why, if you look closely at the cubic, it's always increasing. That's why. Now, let's look at what a critical point is, because that's going to be really important as we go on to like optimization problems, related rates, all that good jazz, right? So a critical point, definition of a critical point. What is that? It's essentially f of x is a point C in the domain such that f prime of C is equal to 0, or f prime of C does not exist. That's what happens. That's what a critical point is. And I'm like, in order for a point to be a critical point, it has to be in the domain, so it has to be the domain of Michael Jackson copy moonwalking. The reason for the importance of critical points is that f of x goes from increase to decrease, or vice versa. You go from increasing to decreasing, or decreasing to increasing at that critical point. So if we test for increase or decrease, that's our new topic, we want to find f prime of x. So we'll find all critical points by equating f prime of x equals 0, and also where f prime of x does not exist. So once you find those are your critical points that you start off with. And then where f prime of x is greater than 0, it's increasing. Where f prime of x is less than 0, it's decreasing. So I think what would really help with this is an example. That would really solidify everything. So if I have f of x equals 2x cubed plus 15x squared minus 36x plus 10, then f prime of x equals 6x squared plus 30x minus 36. And if I want to find when f prime of x equals 0, then I can common factor first. And I would do a product with a sum, a product of -6 and a sum of 5. So that would just be product of -6, sum of 5, 6 and -1. So 6 right there. seems like they use a different values. I guess they use negative -3 and -2. So I don't think he factored that properly, because those wouldn't sum. Because -3 and -2 don't sum to +5. Because that is x squared minus. That's a mistake. So yeah, that's a mistake on their part. The mistake in the notes. So what you would do is that you plot -6 and 1, and you would test for points. This is a derivative, right? Where is it? It's right here. So something less than -6, like -100, I get a big number here. Just do like -7. -7 squared is 49. That's a huge number. Should be positive actually. And then over here, if I put in 0, I get negative. And then if I put in something bigger, I should get positive as well. That's increased, negative, and then decrease and increase essentially. So you write the interval, it's between -infinity and 2 union with, not 2, 6, 1 and infinity. And then decreasing, that's increasing and decreasing from -6 to 1. So that would be the intervals of increase and decrease for that problem right there. I'll give you guys a more straightforward example first before we get too crazy into this. If I have f of x equal to x to the power 2/3, then f prime of x equals 2/3. That -1 is 1/3. So we have 2/3 times the cube root of x. So the undefined point is 0. So at f prime of 0 does not exist, because you'd make a denominator 0, so it wouldn't work. So if we made that number line at 0, f prime is like -1 would be negative, so it's decreasing, and the positive would be increasing. So basically, it's increasing from the interval of 0 to infinity, and it's decreasing from -infinity to 0, essentially. Those would be the values. Right there, basically. Those would be the intervals. So, I think that basically sums it up. Next lecture, we'll be talking about relative max and mins.